Hello everyone, myself Sumit Maheshwari, Assistant Professor in ABES Engineering College, Ghaziabad. Today I am delivering a lecture on derivation of series resonance of a fundamental of electrical engineering subject. So first of all, we can discuss uh, how series resonance occurs and what are the conditions. So if we have a series RLC circuit in which a resistance, a inductor, and a capacitor is connected in series with a single phase AC supply like this. So this is the resistance R. Suppose this is the inductance L and this is the capacitance C. And as per this inductance, the reactance of this inductor is minus J times of XL plus, and for this capacitance, this is minus J times of XC. So this is the R. Voltage V, that is single phase supply. Suppose the supply frequency is F. So if we are thinking about the circuit, the current in these three elements are equal, which is I, because the circuit is uh, series connected. Now, if we are talking about the voltage across R, L, and C, suppose voltage across R is VR, voltage across L is VL, and voltage across C is VC. So what is the relationship between these voltages and the current? So in pure R, in pure resistance, uh, the current I and this VR is in same phase. In inductance, L. So what is the relationship VL and I? If we are taking current as reference, our VL is 90-degree leading. So in inductor, voltage is leading with the current by an angle 90-degree. In capacitor, see, if our current is reference, then voltage across capacitor VC is 90-degree behind with this current. So in such a way, we have three vector VR, VL, and VC. So what is the resultant vector? Resultant vector, that is V supply, is equal to vector sum of these three vector VR plus VL plus VC. If we are taking mode of this vector, so it may be V is equal to under root of VR square plus VL minus VC का whole square. So this is our resultant voltage V. Now we have three conditions. First, when VC is greater than VL. This is the first case. Second case, when VL is greater than VC. And third, when VL is equal to VC. So let us start. First, this is our current vector first. Then we are making second vector VR in the same phase with I. Now this is the VL vector which is leading 90° from this current, and this is our VC which is greater than VL in 90° behind this current. So the resultant vector of VL and VC is called VC minus VL because VC is larger than VL. So this is the vector, and the resultant vector between VR and VC minus VL is resultant V. In the similar way, if VL is greater than VC, then this vector which is uh, lagging behind the current is now leading, and this is our resultant vector VL minus VC, and the resultant of VR vector and VL minus VC. This is VR vector and this is our VL minus VC vector. So the resultant vector of V is OB. Now, if VL is equal to VC, is these two vectors are equal, then our resultant vector is equal to VR. VR is equal to V. So if we are thinking about VL vector is equal to VC in third case, it is possible when VL is equal to I into XL and VC is equal to I into XC. So if voltages are equal and current is always equal because circuit is series connected, then XL is equal to XC. So it is possible XL and XC is possible at a frequency at a frequency when these two reactants are equal. So we can find out the frequency at which XL is equal to XC. Now, this is our resonance curve. So the frequency at which XL is equal to XC, that frequency is called resonant frequency. Now we have XL, that is omega L or 2 pi FL, and we have XC, that is 1 upon 2 pi FC. So if we are thinking about the relationship between XL and frequency, which is proportional, and XC and frequency, which is inversely proportional. So if frequency is increasing, XL is increasing, and if frequency is increasing, XC is decreasing. So for F tending to 0, XL is also tending to 0. If frequency is tending to infinity, XL is also tending to infinity. For XC, if frequency is tending to 0, XC is tending to infinity, or if frequency is tending to infinity, XC is tending to 0. So this is our XL curve, which is proportional to frequency, and this is our minus XC curve. If when we are adding XL minus XC, So at frequency 0, Xc is higher, Xc is high because it is tending to infinity, and at frequency infinity, XL is high. So at the starting, the curve follows Xc, and at the infinity, curve follow XL. So in such a way, this curve XL minus Xc, this XL minus Xc curve, which is called X is at the time of starting, it follows the minus Xc curve, and at the infinity, this is a frequency, at the infinity, it follows XL curve. It's a straight line, like in the first quadrant. So there is a frequency at which resonance occur when XL is equal to Xc. So we need to find out this frequency. Now, if we are taking this XL minus Xc, the mod, so we have taking this curve Z. So when XL is equal to Xc, so Z is under root of R square plus XL minus Xc whole square. So when XL is equal to Xc, Z is equal to R. So which is Z minimum. So at resonance, Z is minimum. So at the starting, it is maximum, and at the end, it is maximum. But at a point where resonance occur, Z is minimum. So in similar way, I which is V by Z, and Z is minimum, then I is called maximum. So at resonance, current is maximum. So this curve for I, and this is I max, Im. So at resonance, our frequency at which resonance occur, our current is maximum. So first of all, we will find out the resonant frequency, and then we will find out these F1 and F2 cutoff frequencies or half power frequencies. So the expression for resonant frequency Fr, at which XL is equal to Xc. So XL, which is omega L and omega RL, and Xc 1 upon omega RC. So omega R square is equal to 1 by LC. Omega R is just 1 upon root LC. Now omega R 2 pi FR, that is 1 by root LC. So FR 1 by 2 pi root LC. So this is our resonant frequency, which is also derived by using cutoff frequencies in terms of F1, F2 later on. So this is our resonant frequency at which XL is equal to Xc. Now we need to find out bandwidth. So if we are taking, this is delta F, and this is also delta F. So what is the bandwidth? Bandwidth, which is twice of delta F, and which is F2 minus F1 that is twice of delta F. So we can use this when we are finding F1, F2. So what is F1 and F2? F1 and F2 are cutoff frequencies, and that is upper half frequency, and F2 is lower half. Sorry, F1 is lower half frequency and F2 is upper half frequency. So we have to find out these frequency and where these frequencies are derived. So we are understanding how we are taking F1 and F2. So we know that our Z at resonance is minimum, which is equal to R, and correspondingly our I current is Im, that is V upon Z minimum, which is equal to V upon R. Now, if we are taking power at resonance, which is P max I square R, because circuit is purely resistive, XL is equal to XC, which is cancel out. So Im square Z minimum, or we can say R, this is our maximum power. Now, what is half power? We are calculating half power such that we can find out the resonant frequency F1, F2. So Pm by 2, that is Im square R by 2, or we can say Im upon root 2 whole square into R. So if we are comparing power at resonance and at power at half power, so the current is I is Im upon root 2. So what is the current? The total current in the circuit I, which is V upon under root of R square plus omega L minus 1 upon omega C whole square, because the current I is equal to V by R is only at resonance, but before resonance and after resonance, the current is I is equal to V upon under root of R square plus omega L minus 1 upon omega C whole square. So put it here, V upon under root of R square plus omega L minus 1 upon omega C whole square. And what is the value of Im? Im is V upon R, that is under root 2 as it is. So if we are squaring of this term, denominator, we are getting R square plus omega L minus 1 upon omega C whole square, which is equal to 2R square. And after solving, it is omega L minus 1 upon omega C whole square is equal to R square. Now we are having two values for F1, F2. So this is our F1 and this is our F2, correspondingly omega 1, omega 2. Now this is our half power. And when we are drawing a line perpendicular, parallel to this x-axis, frequency axis, so it bisect the curve at two places, and we are taking a perpendicular on this x-axis, we are getting this F1 and F2. So this is our delta F. This is also our delta F. And this is our resonant frequency. And these are half power frequencies. So when we are considering omega L minus 1 upon omega C ka whole square is equal to R square, we are having two frequencies correspondingly omega 1, omega 2. So when leaving this square, we are having two values of R. One is plus R, another is minus R. So omega 2 L minus K1 upon omega 2 C is equal to plus R, and omega 1 L minus K1 upon omega 1 C is equal to minus R. Now adding these, this is equation suppose 1 and this is equation 2. Adding equation 1 and 2. So omega 2 plus omega 1 L minus 1 upon C omega 2 plus omega 1 upon omega 1 omega 2 is equal to 0 plus R and minus R, which is 0. Now taking omega 2 plus omega 1 L is common. So here 1 minus 1 upon LC omega 1 omega 2, which is equal to 0. So adding these two, omega 1 plus omega 2 cannot be 0. And L is also not equal to 0. Then this term is only equal to 0. So when we are putting this expression is equal to 0, so we are having LC is equal to 1 upon omega 1 omega 2. So if omega 1 is equal to omega 2 is equal to omega R. So the frequency at FR is, we are taking omega R, angular frequency omega R. So omega R is equal to omega R. So LC is equal to 1 upon omega R square. So omega R is equal to 1 upon root LC, and correspondingly FR 1 upon 2 pi root LC. So this is our resonant frequency expression by taking angular cutoff frequency omega 1 omega 2. Now if we are subtracting these equation 1 and 2, so we have this equation number 1 and this is equation number 2. Now 1 minus 2 equation. So we have getting the expression omega 2 minus omega 1 L minus, if we are taking 1 upon C common, and also minus sign. So this is 1 upon omega 1 plus 1 upon omega 2, and this is uh, 1 upon this is 1 upon omega 1 C minus 1 upon omega 2 C. We are taking not C common here, which is equal to twice of R. So we are taking omega 2 minus omega 1 L is common from this expression. So here this is 1 plus 1 upon C omega 2 minus omega 1, which are taken already outside. So the expression is coming 1 upon omega 1 omega 2, which is equal to twice of R. In previous uh, way, we are calculating here LC is equal to 1 upon omega 1 omega 2. So if we are taking uh, here L is equal to 1 upon omega 1 omega 2 C. So if we are replacing here 1 upon omega 1 omega 2 C is what? L. And here uh, L is also there because we are also taking L outside. So this is our 1. So omega 2 minus omega 1 L is equal to 1 plus 1. This is equal to 1. Or we can say 1 is equal to 1 upon omega 1 omega 2 C LC. This is equal to 1. We are putting here 1 is equal to twice of R. So what is the value of omega 2 minus omega 1 is equal to R by L. This is R by L, and correspondingly for frequency F2 minus F1 is equal to R upon 2 pi L. So this is the difference of cutoff frequencies F2 minus F1. Now we are calculating if we are taking this is delta F. So what are the cutoff frequencies? So here F1, so the whole length till here is FR. If we are subtracting FR minus delta F, we are getting F1. So this is F1 and FR minus delta F. Similarly, what is the F2? F2 is FR plus delta F. So this is our F2 minus F1 delta F. So we are writing here F2 minus F1, that is twice of delta F. So twice of delta F. And what is the value of F2 minus F1? That is R upon 2 pi L. So what is the value of delta F? R upon 4 pi L. And putting here in F1, F2, equation F1 and F2, F1 is Fr minus delta F, which is Fr minus R upon 4 pi L, and F2 is equal to Fr plus delta F, that is Fr plus R upon 4 pi L. So these are the cutoff frequencies F1 and F2. Now we are calculating one more relationship here, quality factor. So what is the quality factor Q? Quality factor Q is equal to VL or VC upon V supply. So what is VL? VL is equal to I into XL. And what is the V supply? V is I into Z. Z is at resonance, I into R. So putting here, Q is equal to I into XL upon I into R. So XL omega R L by R. So this is our first formula of quality factor Q, omega R L upon R. If you are putting here the value of omega R, that is 1 upon root LC into L upon R. So we are getting the another formula of quality factor Q in terms of RLC, 1 upon R under root L by C. Here, if we are multiplying omega R in numerator and denominator, and we have already omega R L by R. So we have the expression here, omega R square L upon omega R into R. So putting here the value of omega R is 1 upon root LC into L upon omega R. So L is cutting out here. The value is 1 upon, and here square is not, because we are taking omega R square. So L to L cancel out. So 1 upon omega R RC. So this is another formula Q, that is 1 upon omega R RC. So if we are giving L and R and omega R, we are using this Q formula. And if we have R, L, and C, these three values, so we are using this formula. And in terms of RC and omega R, we are using this formula. Now, what is the significance of quality factor? So in generally when we are observing the voltage VL, which is equal to VC, but at resonance, this VL or VC is quietly larger than V supply. So if this is quite large, then quality factor is always greater than 1. And we are seeing this called voltage resonance or voltage magnification. Voltage magnification. And the circuit which are using in RLC series circuit is called acceptor circuit. Acceptor circuit, because it are accepting the frequencies between the bandwidth. So the frequency between the delta f, twice of delta f, all the frequencies are accepting and other than frequencies are rejecting. So this is the significance of series resonance. These are our references. We are taking using J.B. Gupta and U.A. Bakshi of Basic Electrical Engineering. These are our disclaimer. Thank you. Next lecture, we are discussing parallel resonance for the same. Thank you.